The following video goes over examples for compositions of functions. So the first thing we're going to talk about is just a review of the previous video. If we have a function, s of t of x, and I substitute x into t of x, I'm going to get some y value. That y value becomes the new x value inside of s. And then whatever comes out of that is going to be the y value on the graph of s of t of x. So that's kind of important. If we're talking about this in terms of like domains, the x value, all the x values that we can sub in, or at least the ones we think we can sub in at the beginning, are d of t, okay, the domain of t of x. And that kind of goes to what we learned last time. The domain of the composition is always at least as restrictive as the domain of the first thing we substitute in. But it could be more restrictive because what happens is as I substitute the domain of t into t, the range of t comes out. But then I may not be able to substitute all of the range of t into this composition because the domain of s has to, like everything that's in the range of t has to fit into the domain of s. So we look and it is the most restrictive combination of the range of t and the domain of s that we can have. So as I look at the range of t in the domain of s, I have to make sure that it's restrictive there. And then what happens is I look at what I get here and I go back to the domain and I have to figure out, do I have to change my domain of t? So I might have to make it smaller, but I'll never make it bigger. So that means that s of t of x is always going to be at least as small as d of t. It's at least as restrictive as the domain of t, but it may be even smaller. All right, so here are some examples. Given f is root 3 minus x, g is 2 over x minus 2, and h is x squared, we're going to find each of the following and state its domain. Well, the first thing we're going to do is we're going to talk about the domain and range of f. So root 3 minus x is that square root function that you're seeing on the screen that has a horizontal reflection and a horizontal translation. 3 to the right, and it flips horizontally. So you're seeing the domain and range of that are pretty clear, negative infinity to 3 and 0 to infinity. G is 2 over x minus 2. That is the rational function that has a vertical asymptote at 0 and a horizontal asymptote. And a vertical asymptote at 2 and a horizontal asymptote at 0. So you're seeing that function here, and the domain is negative infinity to 2 and 2 to infinity, and then the range is negative infinity to 0, 0 to infinity. And then x squared you're seeing on the screen, but you've seen y equals x squared many times in your life. So now if we take a look at g of f is g of root 3 minus x. So I'm going to take root 3 minus x and sub it in for where x is in this function, and this is kind of what it looks like. So now my objective is, what is the domain of this? Well, I know that it is at least as restrictive as the domain of f. So it cannot be any bigger than negative infinity to 3. Or it can't be any bigger than that. So now, are there any other situations where I can't plug something in? And if I look, the denominator is not allowed to be 0. That's true all the time. So that means that I have to do some sort of additional restricting here. Root 3 minus x minus 2 cannot equal 0. And I could solve this algebraically, but just thinking about it, I know that this is negative 1 because 3 minus negative 1 gives me 4. The square root of 4 is 2, and 2 minus 2 is 0. So negative 1 is something that actually restricts my domain even further. So I can't just say negative infinity to 3. I have to say I have an even further restriction, negative infinity to negative 1. union 1 to 3. And that's something that you're going to see in the graph that's put on the screen here. So we're seeing that graph. And while that's happening, we see the domain. When we look at the range compared to the domain, there's obviously something in 0 to infinity that isn't allowed in here. So that means since there's some sort of extra restriction, I have to go back and analyze this domain. And I did, and we found that -1 was the problem. F of g, I take 2 over x minus 2 and sub it in where x is. Okay, so I sub that in where x is. So clearly, the domain cannot be any bigger than -infinity to -2 union, or not -2, +2, union 2 to infinity, because that's the original domain. But if I look, I notice that this is inside of a square root, and that means that I can't have this be less than 0. So I have to kind of analyze this situation, and this is one of the harder things that we're going to have to analyze. So I'm going to actually put this on a separate slide. 3 minus 2 over x minus 2 must be greater than 0. Actually greater than or equal to 0, because we're allowed to have the number underneath the square root be equal to 0. So this represents the number that's underneath the square root. And what we want to do is, I'm going to break it into two cases. The one where x is greater than or equal to 2. The reason why I'm going to break this into two cases is because when I cross multiply, I may or may not have to flip the sign depending on whether what I'm multiplying by is positive or negative. So 3, then I'll add this over to the other side, is greater than or equal to 2 over x minus 2. And if I have 3 is greater than or equal to 2 over x minus 2, what happens if x is less than 2? So these are the two cases that I'm going to take into account. When I cross multiply, if it's greater than 2, x minus 2 is positive, and therefore I don't have to flip the inequality sign. Then I add 2, and I get x is greater than or equal to 8/3. So I have some sort of restriction where x has to be greater than or equal to 8/3, because that's more restrictive than x is greater than or equal to 2. So this is some sort of restriction on the inside of the square root. Now over here, when I cross multiply, I have to flip the sign, because x minus 2, if x is less than 2, is a negative number. And then I add 2, and I get x is less than or equal to 8/3. Well, in this case, this is actually the more restrictive thing, because x is less than 2 is more restrictive than x is less than or equal to 8/3. So if I'm looking at what's on the inside of the square root, I'm allowed to have everything from -infinity to 2 union 8/3 to infinity. So when I go back to this, notice that originally I knew that I wasn't allowed to have 2 be part of the domain. But now what I'm noticing is that this 2 actually has to be replaced with a little bit more restriction. I can't have anything from 2 to 8/3. So my final answer for the domain is going to be -infinity to 2 union 8/3 to infinity. And you're seeing the graph of this on the screen, and you see how from -infinity to 2, you're allowed to plug stuff in, but then from 2 to 8/3, you can't. And then starting at 8/3, this thing equals 0, and then it starts to go up from there. H of f is actually one of the more interesting ones, because you see 3 minus x, but as you can see, I'm going to put the graph on the screen already. 3 minus x actually has some domain restrictions, and the restrictions are -infinity to 3. So even though this looks like there are no issues, because we started with a root 3 minus x, we can't substitute in anything that is bigger than +3, because that would make the thing under the square root negative. So we have a domain restriction, and we saw that at the beginning. Remember that the most, or the restrictions are at least what we started with. So this 0 to infinity fits entirely into negative infinity to infinity. So since it fits entirely in, we don't really have to do anything else other than that. But we do have to make sure that we keep the restrictions that we had to start. Okay. A couple more quick examples that are already worked out. So f of g of x in this 5 over x minus 1 and 4 over 3x minus 2. I substitute 4 over 3x minus 2 into this function. And then I did a lot of simplifying, and I ended up with this thing. But here's what we have to do. In terms of the domain, if we're just caring about the domain, this is probably the easiest way to look at it. If we analyze what's happening, the domain of each of these, the domain of f and the domain of g, had restrictions at 1 and 2/3 originally. So if I look at what's happening, I definitely cannot have the original domain restriction of g because g is the first thing. So I can't have 2/3. But then I can't have the denominator equal to 0 either. And so not only can I not have 2/3, if I do a little bit of simplifying, what I see is that the denominator includes this 2 minus x. And so that means that I also cannot have 2, because if I substitute 2 in, I end up with a 0 in the denominator again. So I originally had a 2/3 restriction, and now I also have a 2 restriction. So this would be negative infinity to 2/3 union 2/3 to 2 union 2 to infinity. So everything except 2/3 and 2. And you also could get that just from simplifying the denominator and making sure that that wasn't equal to 0. So if you add 1, cross multiply, and do all the other stuff, what you would have found is you would have got 2. Likewise, the same thing is happening over here, but I'm going to talk through it a little bit faster because I just said what was happening. Clearly, we can't substitute 1 in. That was the original domain restriction. But when I simplify, I end up with 17 minus 2x in the denominator, or I could have just taken this, set it equal to 0, and solved and found out something else I can't have in the denominator because the entire denominator is not allowed to be 0. But what I see is 17 halves is something that I'm not allowed to have. So the domain is negative infinity to 1 union 1 to 17 halves union 17 halves to infinity. Finally, if I have these functions, f of g is substituting root x minus 4 in where x is. So I have 1 over root x minus 4. The original domain of these functions is a not equal 0 and a greater than or equal to 4. So these are x's. So now when I look at this, I have the original domain restriction of g, which is x's between 4 and infinity. But now when I look at this, I can't have the denominator equal 0, which means if I actually substitute in x equals 4, I get a problem. So notice that there's some sort of slight distinction that I have to make. The final answer is not going to be 4 to infinity. It's going to be parentheses 4 to infinity, because I'm not allowed to substitute that 4 in. In this case, I'm substituting 1 over x in where x was. The original domain of f, which is the inside function, was not equal to 0. So negative infinity to 0 union 0 to infinity was my original one. But now when I look at this, I also have another situation that's happening. The inside of this is not, I can't have 0 on the inside or anything less than 0. So 1 over x minus 4 must be greater than 0. So 1 over x is greater than 4. And now I end up with the exact same situation that I had earlier, where I have to break this into two cases: if x is greater than or equal to 0, or if x is less than 0. So if x is greater than or equal to 0, and I cross multiply, I don't have to flip the sign. These are greater than or equal to, sorry. So x has to be less than or equal to 1/4. Likewise, if I have 1 over x is greater than or equal to 4, but x is less than 0, when I cross multiply, I have to flip the sign. So x is greater than 1/4. This is more restrictive on the right side, and this is more restrictive on the left side, which means that I have to change this to be 1/4 in order to get my final answer. So I have negative infinity to 0, union 1/4 with a bracket to infinity.